Hello there, and welcome back to the Quantum Slumber. Tonight, I want to begin with a claim that sounds impossible, and yet sits disturbingly close to the heart of the modern physics. You may not exist in the way you think you do, not because your mind is secretly manifesting the universe, and not because reality is a dream you can control, but because at the deepest level, physics no longer describes a world made of solid, separate things with fixed properties quietly waiting to be discovered. Instead, it points towards something stranger, a world in which a particle may not possess a definite property until measurement forces an outcome. A world in which matter is not truly made of little objects, but of excitations in invisible fields. A world in which empty space is not empty, and separation may not be as fundamental as it feels. And if that is true, then the question is no longer just what the universe is made of. The deeper question is what it means for anything to exist at all. Tonight, we are going to move through that question slowly, carefully, and honestly. Not to force a mystical answer, not to dress physics up as self-help, but to sit with one of the deepest mysteries science has ever uncovered. Whether reality is fully settled before it is observed, whether the world is made of things at all, and whether being itself is far more relational, unstable, and unfinished than human intuition ever imagined. So, if you enjoy these slow journeys into the deeper edges of science, gently give the video a like, subscribe to the channel, and let me know in the comments where you're listening from tonight. Now, let the ordinary picture of reality soften a little, and let's begin. When most of us think about reality, we imagine that the world is already finished before we arrive. We assume that things possess their properties quietly and completely, whether anyone looks at them or not. A chair is in the room, even if the lights are off. A coin lying under a blanket is already heads or tails before the blanket is lifted. A gift in wrapping paper already contains what it contains before the ribbon is untied. In ordinary life, this assumption feels so natural that it hardly even appears as an assumption. It feels like common sense. And for the world of ordinary objects, common sense works well enough. It helps us move through rooms without walking into walls. It helps us trust that the coffee cup is still on the table when we turn our backs. It helps us believe that reality is stable, settled, and waiting for us in a fully formed state. But at the quantum level, that picture begins to fracture. What modern physics discovered, with enormous reluctance and extraordinary precision, is that the smallest constituents of nature do not seem to behave like tiny hidden objects carrying definite properties around with them in the dark. They do not behave like miniature stones or miniature marbles, each with a position, a path, and a set of built-in attributes merely awaiting discovery. Instead, the formalism of quantum mechanics points towards something much harder for the mind to hold. It suggests that, before measurement, certain properties may not exist in a definite form at all. That statement has to be handled carefully because it is often distorted into something childish or mystical. It does not mean that human wishes control the universe. It does not mean the world is a dream generated by personal belief. And it does not mean physics has proven some motivational slogan about creating your own reality. The claim is stranger than that, and more austere. The claim is that, for a quantum system, asking what value a property has before measurement may not always be like asking what is inside a wrapped present before you open it. In the ordinary picture, the present is already full. The paper only hides what is there. In the quantum picture, at least in the standard reading, the situation is more unsettling. The box is not merely closed. The content may not yet be definite in the classical sense at all. This is the point where people often retreat into familiar language and say, well, maybe the property is there, we just don't know it yet. That sounds reasonable. It preserves the old world view. It lets us keep the comforting sense that the universe is made of things with hidden labels attached to them, and that science is simply the process of peeling those labels back. But the Copenhagen tradition, the interpretation that shaped the teaching of quantum mechanics for generations, does not describe the situation in those terms. In that view, the issue is not ignorance. The issue is indeterminacy. That difference matters. Ignorance means there is already a fact, but you do not yet possess it. If a card is face down on a table, it is still the Queen of Hearts or the Seven of Clubs even before you flip it over. Your lack of knowledge does not make the card indefinite. The fact is settled. Your mind is simply late to it. But quantum mechanics, read in its standard way, does not always allow that kind of hidden certainty. Before measurement, the electron is not necessarily sitting somewhere specific with a definite position that you merely haven't uncovered. The system is described by a wave function, and that wave function does not give you a single settled answer. It gives you a range of possible outcomes with definite mathematical weights. And here's the difficult part. In the orthodox reading, those possibilities are not just placeholders for ignorance. They are not little envelopes containing unknown pre-written answers. They are the actual content of the physical description. This is why the problem is so deep. Because the challenge is not merely technical, it is ontological. It forces us to ask what kind of existence we are dealing with, when the most successful theory in physics does not describe a tiny object with a fully determined set of hidden properties, but a spread of possibilities that only become definite when a measurement occurs. That is not fringe physics. That is not a strange side road built by internet speculation. It is the center of the modern quantum story. For nearly a century, students in physics departments around the world have been taught to calculate using this machinery because it works with astonishing accuracy. The predictions of quantum mechanics are not vaguely right. They are precise beyond ordinary comprehension. Again and again, the mathematics lands exactly where experiment says it should. The theory is not in trouble because it fails to predict. The theory is in trouble because it predicts beautifully while leaving us unsure what the prediction says reality actually is. That is the first real crack. Not that the equations fail, the equations succeed too well. The crack appears because the equations succeed without restoring the old image of a world made of self-contained little things with fixed internal properties. They succeed while asking us to accept that the underlying reality may be less like a collection of finished facts and more like a structure of possibilities awaiting an event that forces one of them into view. This is where the phrase measurement problem begins to matter. Because measurement in classical physics is simple, a thermometer reveals the temperature, a ruler reveals the length, a camera reveals the position of an object already sitting there in space. Measurement is passive. The world is complete. The instrument merely reports it. Classical measurement is a window. Quantum measurement does not behave like a window. It behaves more like an intervention, or at the very least like an event that cannot be separated cleanly from the thing being measured. The property you end up with after the measurement is definite. The description you had before the measurement was not. So, the natural question arises with enormous force. What changed? What happened in the act of measurement that turned a spread of possibilities into one actual result? That question is not decorative philosophy sitting politely outside physics. It is built into the heart of the subject. Because if a property is not definite before measurement and is definite after measurement, then measurement is not merely revealing a world that was already settled. It is participating, somehow, in the production of settledness. And once you say that carefully, another question appears right behind it. What does it mean for something to exist if its properties are not fully fixed before it is measured? Not metaphorically, not spiritually, literally. What is a thing if its measurable features are not simply sitting there in advance like labels attached to a suitcase? The older picture of existence was simple. A thing existed first, and then it had properties. It had a location, momentum, size, state. Knowledge came later, physics uncovered what was already there. But the quantum picture unsettles that order. Now, existence itself begins to look less like a finished possession and more like a structured openness. Less like a noun and more like a waiting pattern. Less like a tiny object and more like a set of allowed outcomes held in suspension until the world is forced into specificity. This is why quantum mechanics has never felt merely technical to the people who thought hardest about it. Einstein did not resist it because he was confused by the math. Bohr did not defend it because he enjoyed obscurity. They both understood that something far larger than calculation was at stake. What they were arguing over was not just how to solve atomic problems. They were arguing over what sort of world we inhabit. A world of hidden facts, or a world in which, at the deepest level, not every fact is there in the ordinary sense before the universe is asked a precise question. You can feel how radical that is if you pause long enough, because the mind wants to rush back towards stable ground. It wants to say that surely the moon is there whether or not we look. Surely the electron must be somewhere whether or not we measure it. Surely reality cannot depend so heavily on an act of inquiry. And perhaps, in some deeper interpretation yet to be agreed upon, some of that comfort may one day be restored. But the standard formalism, taken seriously on its own terms, does not hand that comfort to us for free. It gives us results. It gives us extraordinary predictive power. But it also gives us a world that, at its most fundamental scale, may not come with all its properties pre-written. And that is where the ground first begins to move. Not when we start talking about consciousness, not when we start talking about spirituality, not when popular culture starts dressing quantum theory in mystical language. The true disturbance arrives earlier, closer to the mathematics itself, at the moment we realize that measurement in quantum mechanics may not simply reveal what is there. It may be part of how definite reality appears at all. Of all the experiments in modern physics, there is one that has been stretched, simplified, romanticized, and misunderstood more than almost any other. It appears in documentaries, podcasts, self-help books, spiritual seminars, and late-night conversations whenever people want to say that science has finally discovered something magical. It is treated as proof that the mind changes matter, that thought shapes the world, that consciousness reaches outward and sculpts reality simply by looking. What they are almost always talking about is the double-slit experiment. And the reason this experiment survives every retelling is that even in its cleanest, most sober form, it is genuinely unsettling. Not because it proves that human intention controls the universe. It does not. Not because it shows that awareness is a cosmic superpower. It does not. It survives because it reveals something quieter and more disturbing than that. It reveals that the act we call observation in physics is not as passive as common sense wants it to be. Imagine a barrier with two narrow openings cut into it, and behind that barrier, a screen. Now imagine firing tiny entities toward those openings. You can use photons. You can use electrons. You can even do versions of this with larger molecules. If you think classically, you would expect something simple. If each particle is a little object, then each one should go through either the left slit or the right slit. Over time, the screen behind should show two bright bands, one behind each opening, as though you had tossed tiny pellets through two narrow gates. That is not what happens when you leave the system alone. When no measurement is made to determine which slit the particle passes through, the screen does not show two neat bands. It shows an interference pattern, alternating bright and dark stripes, the same sort of pattern produced by waves. Light waves do this. Water waves do this. A crest meets a crest and builds. A crest meets a trough and cancels. The result is a pattern of reinforcement and subtraction, a structure that only makes sense if something wave-like has passed through both slits and interfered with itself. That alone is strange enough, but the experiment becomes truly unforgettable when you decide to ask a more pointed question. Which slit did the particle go through? The moment you place a detector near the slits, or arrange the apparatus in such a way that path information becomes available, the interference pattern disappears. The screen no longer records the graceful stripe signature of a wave spread across two openings. Instead, it shows the distribution you would expect from particles choosing one slit or the other. The behavior changes when you measure the path. This is the point where the popular story usually takes over. The story says that consciousness is the special ingredient. A human observer looks, and reality obediently rearranges itself. The particle senses awareness. The the universe responds to being watched. Mind collapses the wave function. And from there, the leap into fantasy is easy. If the mind can make a photon become a particle, maybe your thoughts can attract money, alter traffic, heal disease, or summon destiny. But that is not what the physics says. In physics, observation does not mean human attention in the ordinary sense. It does not mean a conscious person standing nearby with curiosity in their mind. It means something much more precise and much less flattering to the ego. It means a physical interaction that leaves a trace. To find out which slit a particle goes through, you cannot merely wonder about it. You must couple the particle to some apparatus. You must shine light on it, scatter another particle off it, place a detector nearby, or otherwise create an exchange of energy, momentum, or information. That interaction matters. If you use a photon to detect the path of an electron, that photon does not politely peak and then drift away without consequence. It hits. It transfers momentum. It changes the system. If you place a detector at one slit, the detector is not a transparent witness floating outside the experiment. It becomes part of the experiment. It couples to the system. It marks the path. And once that path information exists in principle, the interference pattern is lost. So, the first correction is this. The double-slit experiment does not show that consciousness collapses the wave function. It shows that acquiring which path information through physical interaction destroys the phase relationships required for interference. That is the textbook explanation. It is the explanation most working physicists would give if you asked them plainly. And within its proper scope, it is correct. That distinction is important because it clears away a great deal of noise. The universe is not reacting to your personal awareness in the way a stage actor reacts to applause. A detector with no feelings, no self, no inner life can destroy interference perfectly well. A piece of apparatus can do the job. A bit of scattered light can do the job. A single interaction can do the job. You do not need intention. You do not need selfhood. You do not need meditation. You need coupling. And yet, once that clarification is made, the mystery does not vanish. It sharpens, because the ordinary explanation tells you how interference is lost. But it does not fully settle what the particle was before the measurement, or what exactly changes when the measurement occurs. It tells you that path detection disrupts the conditions under which the wave-like pattern can appear. It tells you that measurement involves intervention, not detached viewing, but it still leaves standing the deeper question that made the experiment famous in the first place. What exactly is being observed? If the particle truly had a definite path all along, hidden from us but already fixed, then one might hope that the detector simply reveals that pre-existing fact. But the formalism of quantum mechanics resists that comforting interpretation. Before the path measurement, the system is described in a way that allows both routes to contribute to the final pattern, not as a loose poetic image, but as a calculable structure whose consequences show up on the screen with extraordinary reliability. That is why the interference pattern matters so much. It is not a decorative curiosity. It is evidence that the underlying description cannot be reduced, at least not easily, to the old picture of a tiny object taking one secret route while we remain ignorant of it. The pattern behaves as though the alternatives remain physically relevant until the measurement setup forces a different kind of answer from nature. This is where careful language becomes essential. People often say, the particle goes through both slits. That can be a useful shorthand, but it is also dangerous because it smuggles ordinary imagery into a domain where ordinary imagery tends to break. The particle is not literally a tiny bead split in half, like a grain of sand passing through two doorways at once. What quantum mechanics gives you is a wave function whose evolution includes contributions associated with both paths. Those contributions combine, and that combination produces the interference pattern. Then, when path information is extracted, the pattern changes. Not because the universe has been embarrassed by your gaze, but because the physical conditions that sustain the interference are no longer intact. So, the real lesson is more disciplined and more profound than the pop version. Observation in quantum mechanics is not passive spectatorship. It is an event. It is a physical transaction. It is an act that cannot always be cleanly separated from the reality it interrogates. In classical physics, a measurement can often be imagined as a gentle glance at a world already fully formed. In quantum physics, that image becomes unreliable. To ask a precise question is to alter the terms under which nature can answer. And once you see that clearly, the double-slit experiment stops being a cheap slogan about mind power and becomes what it really is: a warning that the old boundary between the observer and the observed is thinner than common sense expected. Still, even that does not take us all the way down. Because if a detector is enough to alter the outcome, then the detector itself must be included in the physical story. It cannot remain a magical black box standing outside the mathematics. And once you grant that, a harder question begins to form. The particle interacts with the detector, yes. But the detector is also made of atoms. It is also part of the quantum world. It is not some divine exception to the rules, which means the mystery has only moved inward toward a place where the equations become even more difficult to interpret, and the idea of collapse becomes much harder to localize. That is where the simple explanation starts to run out. The ordinary explanation of measurement gives you a mechanism, but it does not give you a stopping point. It tells you that a detector can destroy interference because the detector interacts with the particle. That is true. It tells you that path information can become available through a physical exchange of energy or momentum. That is also true. But once you accept that account, a more difficult question begins to press against it. What exactly is a detector? It is very tempting to imagine the detector as a kind of final authority, a device that turns quantum ambiguity into classical certainty simply by existing. A Geiger counter clicks, a photomultiplier tube flashes, a screen records a spot. The event seems finished, the particle has been measured, the story appears complete. But the detector is not outside physics. It is not made of some special non-quantum substance. It is made of atoms. Its atoms are made of electrons, nuclei, and fields. It belongs to the same physical universe as the particle it is detecting. That means the detector, too, should obey quantum mechanics. The detector, too, should be describable by the same formalism. And once you insist on that consistency, the neat textbook picture begins to unravel. This is where one of the most important and least emotionally satisfying ideas in the foundations of quantum mechanics enters the scene. It is known as the von Neumann chain, after John von Neumann, the brilliant Hungarian-American mathematician who saw with unusual clarity that the problem of measurement could not simply be dismissed by pointing to a machine. Suppose a particle approaches a measuring device. Before any measurement, the particle is described by a quantum state that allows multiple possible outcomes. Perhaps it could be detected at location A or location B. Perhaps it could be associated with slit A or slit B. When the detector interacts with the particle, common language says that the detector finds out the answer. But the Schrödinger equation, applied honestly, does not say that the detector magically extracts one definite outcome and ends the story there. It says something more awkward. It says that the particle and the detector become correlated. If the particle has outcome A, the detector records A. If the particle has outcome B, the detector records B. And if the incoming quantum state allows both possibilities, then the combined state of particle plus detector becomes a superposition of both correlated outcomes. In one term, the particle is A, and the detector says A. In the other term, the particle is B, and the detector says B. The detector has not, in the mathematics, ended the superposition. It has joined it. This is the heart of the problem. The machine that was supposed to resolve the ambiguity has instead become entangled with the ambiguity. The uncertainty has not been destroyed. It has spread. It has moved from the particle alone to the larger system composed of particle and apparatus. Now imagine that a second device records what the first detector says. The same logic applies again. The second device becomes correlated with the first. If the first device recorded A, the second records A. If the first recorded B, the second records B. The superposition extends further. Add a camera observing the apparatus. Add a computer storing the result. Add your eye receiving the light from the screen. Add your brain processing the signal. At each step, the formal structure does not suddenly generate a unique outcome by itself. It produces a larger and larger correlated state. The chain keeps going. Particle, detector, recording device, eye, brain. Each link becomes tied to the previous one. Each link can be treated as part of a single quantum system. And nowhere in the standard unitary evolution of the wave function does the mathematics plainly announce, here. Here is the exact place where possibilities end and one actual world begins. That absence is not a minor technical inconvenience. It is the central wound, because your experience is not a superposition. You do not wake up and see a detector that both clicked and did not click in the same conscious moment. You do not experience a screen that simultaneously displays two incompatible outcomes. You encounter one result, one mark, one reading, one branch of experience, if that language is allowed. Whatever the equations say about the evolving physical state, lived awareness arrives as definite. So now the question becomes unavoidable. Where does definiteness enter? Does it enter at the level of the detector? If so, why there? The detector is quantum too. Does it enter at the level of the eye? The eye is made of molecules, photons, electrochemical processes. Does it enter at the level of the brain? The brain is warm, biological matter, but still matter, still physical, still composed of systems that, at least in principle, ought to be describable by the same laws. Does it enter at the level of consciousness itself? That suggestion has tempted some thinkers, disturbed others, and satisfied almost no one completely. Von Neumann's insight was not that he had solved the problem. It was that he had exposed how deep the problem really is. If every component of the measuring setup is treated as a quantum object, then the usual story about the detector measured it does not finish the job. It only pushes the burden one step further down the line, then another step, then another. The collapse, if collapse is truly what happens, does not emerge naturally from the Schrödinger evolution alone. It seems to be inserted from outside, that evolution as an additional rule. And this is why the measurement problem has never gone away. People sometimes speak as if it were a relic from the early 20th century, a philosophical headache now safely absorbed by modern physics. But that is not true. Quantum mechanics works magnificently as a calculational scheme. It predicts outcomes with astonishing success. Yet the link between the mathematical description and the single definite world of experience remains conceptually unsettled. We know how to calculate. We do not agree on what the calculation means. That distinction is easy to miss, especially in a culture that tends to confuse successful prediction with complete understanding. You can know how to use an equation without knowing what kind of reality the equation describes. You can build lasers, semiconductors, and quantum devices while still arguing about whether the wave function is real, whether it collapses, whether it branches, whether it represents knowledge, or whether some deeper physical mechanism has not yet been found. Engineering can proceed while ontology remains wounded. The von Neumann chain forces that wound into the open. Because once the detector is no longer treated as an unquestioned classical box, the comforting division between the quantum system and the classical observer becomes unstable. Where is the border? At what scale does the world cease to be quantum and become classical? At what stage does possibility harden into fact? The theory itself does not draw that line with anything like universal clarity. And if the theory does not tell you where the line is, then every attempt to speak confidently about what is happening during measurement becomes, in some sense, an interpretation rather than a deduction. This is also the point where many popular distortions of quantum mechanics become seductive. Faced with a real unresolved difficulty, people rush in with premature answers. Some say consciousness must be the key. Some say the entire universe splits. Some say collapse is physical and objective. Some say the wave function is merely a bookkeeping device for expectation. The sheer variety of these responses is not a sign that the problem is fake. It is a sign that the problem is genuine. If the matter were simple, the interpretations would not diverge so radically. At a deeper level, what is at stake here is not merely a question about laboratory procedure. It is a question about what counts as a fact. A fact in ordinary life feels immediate and self-contained. The detector clicked, the coin landed, the light turned on. But the von Neumann chain suggests that inside the formalism of quantum theory, what we call a fact may not be so primitive. It may depend on where we place the cut between system and observer. It may depend on how we treat the measuring apparatus. It may depend on whether we believe collapse is real, apparent, relational, subjective, or still physically unexplained. That is a disturbing thought, because it means the world of finished standalone facts may not be as basic as we once assumed. What we want is a simple answer to a simple question. When does the universe stop entertaining alternatives and commit to one result? But quantum mechanics, in its raw mathematical form, is strangely reluctant to supply that answer. It evolves possibilities forward with impeccable discipline. Then, when an actual measurement occurs, we introduce a second kind of rule to account for the definite result. The tension between those two descriptions has been present from the beginning, and once you see it clearly, you cannot unsee it. The collapse is not cleanly derived from the ordinary dynamical equations. The certainty of experience is not straightforwardly mirrored in the superposed evolution of the formalism. Somewhere between the quantum description and the world as it appears, something unresolved remains. That unresolved thing is not a fringe curiosity. It is the reason quantum mechanics still gives rise to radically different pictures of reality, all built on the same experimental successes, all trying to answer the same stubborn question. What is the world actually doing when a measurement takes place? Once you see that the equations do not quietly produce a single experienced world on their own, a strange landscape opens up. The experiments remain the same, the mathematics remains the same, the predictions remain the same, but the meaning of it all begins to split into radically different visions of reality. This is one of the most fascinating features of quantum mechanics. Physicists do not disagree because some of them accept the data and others reject it. They disagree because the data are so precise, and yet the underlying picture of what the data imply is still unsettled. Quantum mechanics is not a failed theory. It is a triumphant theory with an unresolved ontology. And so, the question becomes, if the formalism works, but the collapse is not plainly derived from the ordinary evolution of the wave function, what are we supposed to think is really happening? One answer, the oldest and still the most widely taught, is the Copenhagen interpretation. It is less a single doctrine than a family resemblance, but its central attitude is recognizable. Before measurement, the quantum state does not describe a tiny object carrying hidden classical properties in secret. It describes a set of possible outcomes and the probabilities associated with them. The wave function is not a photograph of a miniature particle world, unfolding behind the scenes in ordinary space and time. It is a mathematical structure that tells you what may occur when a measurement is made. In this view, asking what the particle was really doing before the measurement can be a mistake, not because the answer is difficult, but because the question itself may be improperly formed. Niels Bohr, who did more than almost anyone to shape this way of thinking, insisted that quantum phenomena do not fit neatly into the old categories of ordinary language. Wave and particle are not two costumes worn by a single familiar object. They are two partial classical descriptions drawn from mutually exclusive experimental arrangements. You can ask a wave-like question, or you can ask a particle-like question, but there may be no deeper classical picture hiding underneath that lets you have both at once. This is Bohr's principle of complementarity. It does not say reality is irrational. It says our inherited language was built for the middle-sized world of tables, rocks, and moving bodies. and that language starts to fail when pushed down to the quantum level. A quantum entity is not secretly a little billiard ball that sometimes pretends to be a wave, nor is it secretly a wave that sometimes pretends to be a particle. It is something for which our everyday conceptual tools are only imperfect handles. The Copenhagen spirit accepts that limitation and refuses to go further than the formalism requires. Measurement yields an outcome. Before measurement, there is no fully classical fact of the matter to uncover. That answer has a certain severity to it. It is disciplined. It is careful. But it also leaves many people unsatisfied because it can sound like an instruction to stop asking what is really real. A very different response came from Hugh Everett in 1957. Instead of modifying the mathematics or treating collapse as a special event, Everett proposed something far more extravagant in scope and, in one sense, more conservative in its treatment of the equations. Take the Schrödinger evolution seriously at every stage, he said. Never add collapse. Never insert a special rule. Let the wave function evolve smoothly and universally. If you do that, then when a measurement occurs, the superposition does not end. It branches. What you call an outcome is simply your own inclusion within one branch of a larger quantum state. In one branch, the detector records one result and the observer sees that result. In another branch, the detector records a different result and a different version of the observer sees that one. Nothing is eliminated. Nothing is singled out by a mysterious collapse. The universe simply contains all the outcomes, each realized in a different branch of the total state. This is the many worlds interpretation. Its appeal is obvious. It removes the special, unexplained collapse postulate. It preserves the mathematical evolution without interruption. It treats the wave function as fully real and universal. But the price is enormous. Reality becomes unimaginably vast. Every quantum event with multiple possible outcomes contributes to a continual branching structure. The world you experience is only one thread in an inconceivably large quantum tree. To some physicists, that is not a reductio ad absurdum. It is the cleanest available reading of the formalism. To others, it feels like a metaphysical overpayment, an attempt to avoid one mystery by multiplying reality beyond all ordinary intuition. A third family of ideas refuses both the Copenhagen restraint and the Everettian branching, and instead says, collapse is real, not apparent, not subjective, not merely epistemic, real, physical. Something in nature itself forces superpositions to end under specific conditions. These are known as objective collapse theories. One influential example is GRW, named after Gherardi, Rimini, and Weber. In that framework, quantum systems evolve mostly according to the usual Schrödinger equation, but occasionally and spontaneously undergo random collapses. For a single microscopic particle, such collapses are exceedingly rare. For macroscopic systems made of vast numbers of particles, the effective collapse becomes overwhelmingly rapid. The theory is designed so that ordinary objects come out definite, while microscopic systems retain their familiar quantum behavior most of the time. Roger Penrose proposed a related but distinct possibility. He suggested that gravity may play a role in ending superpositions. If a quantum state involves two significantly different mass distributions, then the corresponding space-time geometries are also in tension. That tension, he argued, may be unstable. Nature may not permit such gravitationally distinct superpositions to persist indefinitely. At some threshold, the state objectively reduces to a single outcome. These proposals have a special appeal because they do not merely reinterpret the mathematics. They change the physics in principle and therefore invite experiment. If objective collapse is true, then under sufficiently delicate conditions, one might detect deviations from standard quantum predictions. That makes these ideas scientifically attractive, even to those who remain uncertain about their truth. Then there is cubism, which heads in almost the opposite direction. Cubism, or quantum Bausianism, does not treat the wave function as a direct representation of an objective physical state out there in the world. It treats the wave function as an agent's personal assignment of expectations about future experiences. In this view, when you write down a quantum state, you are not describing what a particle is in itself. You are encoding what you expect will happen if you interact with it in a certain way. Collapse, then, is not a physical jump in the external world. It is an update in your expectations after you obtain new information, much like Bayesian updating in probability theory. The drama shifts from ontology to agency. Quantum mechanics becomes, in this reading, a user's manual for how an agent should organize their expectations about encounters with reality. That does not mean cubism denies an external world. Its advocates are careful about that. The world is still there. It resists, it surprises, it pushes back. But the wave function is not a portrait of that world independent of any observer. It is a tool for navigating one's relationship to it. Some find this elegant, even liberating. Others feel it retreats too far from the original question. If the wave function is not describing reality directly, then what is? And that is the remarkable thing. These interpretations are not small variations in mood. They are profoundly different pictures of existence. In Copenhagen, the world is not fully describable between measurements in classical terms, and the question of underlying reality is sharply constrained. In many worlds, reality never collapses, and every allowed outcome persists in branching form. In objective collapse theories, nature itself selects outcomes through a real physical process not contained in ordinary unitary evolution. In cubism, the wave function tracks expectation rather than a detached physical state. Same experiments, same equations at the operational level, radically different ontologies. That is not a weakness of quantum mechanics in the everyday practical sense. It is a sign that we have reached a layer of reality where predictive success outruns conceptual comfort. The theory tells us, with unmatched accuracy, what to expect. It does not force a single consensus about what expectation is expectation of. And once you understand that, the measurement problem stops looking like a minor footnote. It becomes what it really is. A pressure point, where physics turns into metaphysics whether it wants to or not. There is a thought experiment in quantum mechanics that feels almost designed to make the ground give way beneath your feet. It does not rely on vague spiritual language. It does not depend on motivational slogans. It comes from one of the most serious physicists of the 20th century, Eugene Wigner, and it takes the measurement problem and turns it inward with unnerving precision. Imagine a sealed laboratory. Inside the laboratory, a physicist performs a quantum measurement. She looks at the apparatus, records a result, and experiences a definite outcome. For her, the event is finished. The particle was measured. The answer is real. It is written in the notebook. If the outcome was spin up, then spin up is what she saw, what she remembered, and what she would report if asked. Now imagine Wigner outside the lab. He has not opened the door. He has not seen the notebook. He has not interacted with the apparatus inside. If he treats the entire laboratory as one physical system, then according to the ordinary quantum formalism, he may still describe the whole thing as a superposition. The particle in one outcome, the friend seeing that outcome, the notebook recording that outcome, together with the alternative outcome, the friend seeing that one, the notebook recording that one. Inside the lab, there is a definite experience. Outside the lab, there is still a quantum description that has not obviously selected one branch. That is the tension. Wigner's point was not that he had discovered an easy solution. His point was that if quantum mechanics is applied universally, then the distinction between an observed result and an uncollapsed quantum state becomes much harder to localize than physicists sometimes pretend. His friend experiences certainty. Wigner, from the outside, can still write down a superposed description. Both descriptions seem licensed by the theory, and yet they do not sit together comfortably. This is where consciousness entered the discussion in a more careful way than it usually does in popular culture. Wigner did not mean that your wishes shape reality like a personal magic field. He meant something narrower and more technical. If the entire chain of physical systems can, in principle, be treated quantum mechanically, then perhaps the only place where a definite outcome is undeniably present is at the level of conscious experience itself. That idea has never been widely accepted as the final answer, but it was not frivolous. It came from a real pressure point in the formalism. Still, most physicists today do not think consciousness is needed to explain why the macroscopic world appears definite. The dominant response has been decoherence, and decoherence is not a hand-waving escape. It is one of the most important developments in modern quantum theory. To understand it, picture a fragile quantum superposition as something that depends on an exquisitely delicate phase relationship between alternatives. As long as the system remains well isolated, those phase relations are preserved, and the different possibilities can continue to interfere. That is what makes the double-slit pattern possible. But the world around any realistic system is not quiet. It is crowded, busy, thermally active, and full of unavoidable interaction. Photons strike surfaces, air molecules collide, heat radiates, fields fluctuate, information leaks. The moment a quantum system becomes entangled with its environment in enough detail, those delicate phase relations are effectively dispersed into an enormous number of surrounding degrees of freedom. The coherence is not smashed by some mystical force. It is diluted into the world. The alternatives stop behaving like a clean, isolated quantum superposition and begin to behave like effectively classical possibilities. That is decoherence. It explains with immense power why cats, measuring devices, chairs, dust particles, and brains do not seem to display obvious quantum interference in daily life. A microscopic system can remain coherent under carefully controlled conditions. A macroscopic system in a warm environment loses coherence extraordinarily fast. For something the size of a dust grain, the timescale can be fantastically tiny. For anything like a human brain, bathed in heat and ceaseless biochemical activity, coherence at the level needed for large-scale quantum superpositions is destroyed almost immediately. This matters because it undercuts one of the lazier claims often made in popular quantum talk. You do not need a human mind to make the classical world appear classical. The environment is enough. Long before a conscious thought forms, the system has already become entangled with countless external degrees of freedom. Long before a neuron fires in awareness, the surrounding world has done the relevant physical work. In that sense, decoherence is a devastating correction to the claim that consciousness must be the ordinary engine of collapse. And yet, even here, honesty requires a pause. Decoherence is powerful, but it is not the same as a full solution to the measurement problem. What decoherence explains is why interference between macroscopically distinct alternatives becomes effectively unobservable. It explains why the branches stop talking to each other, why the world looks classical, why you do not watch your coffee cup smear itself across multiple locations. But it does not by itself explain why one particular outcome is the one you experience. It changes the shape of the mystery. It does not erase the mystery. After decoherence, you may have a set of effectively non-interfering branches, or a diagonalized density matrix, or a world in which alternatives no longer combine in any practical sense. But the old question can still return in a quieter voice. Why this result rather than that one? Why this experienced fact? Why one actual reading instead of a merely formal spread of possibilities? That is why the measurement problem remains alive. Consciousness creates reality is too strong. Standard physics does not establish that. Consciousness is obviously irrelevant, is also more confident than the foundations strictly permit. Decoherence explains a great deal, but not everything. Wigner's proposal is not the consensus view, but neither did it arise from foolishness. It arose because the theory, read carefully, leaves a genuine opening where the relation between physical process and definite experience is still not fully understood. So, the most honest position is not triumph and not dismissal. It is restraint, We know that the classical world emerges from quantum physics in ways that decoherence helps illuminate. We know that consciousness is not required in the ordinary textbook account of measurement as physical interaction. We also know that when we ask exactly how one experienced outcome appears from the formalism, the foundations become less settled than many people realize. And so, the deepest answer, at least for now, remains the simplest one to say and the hardest one to accept. We do not know. Up to this point, the disturbance has been centered on knowledge, on measurement, on the uneasy possibility that a property may not be fully definite until an interaction forces the world to answer in one particular way. That alone is enough to loosen the mind's grip on ordinary intuition. But there is a deeper layer beneath it, and in some ways, it is even harder to absorb. Because once the question of measurement has done its work, another question begins to rise behind it. Not how a property becomes definite, not where collapse happens, but what exactly is the thing that is being measured in the first place? Most of us carry around a picture of matter that was formed so early we no longer notice it. We imagine objects as little islands of substance, small, durable units, solid pieces of reality occupying space, persisting through time, and retaining some inner core of thingness no matter how much science refines the details. Even if we accept atoms, and even if we accept subatomic particles, we still tend to picture the world as built from ever smaller objects, tiny bits of stuff all the way down. That picture is useful in daily life. It is also, at the deepest level, wrong. And this is where the strangeness of quantum physics changes character. The first half of the mystery was about whether reality is fully settled before it is observed. The next half is about whether reality is made of things at all. That shift matters because it changes the emotional texture of the question. Before, the discomfort came from uncertainty. Now it comes from ontology, from the possibility that the universe is not built from independent little units of matter in the way common sense still imagines, but from something more continuous, more abstract, and more difficult to picture. If that sounds like philosophy drifting away from physics, it is not. It is physics becoming more honest about what its equations actually describe. The older mechanical worldview, the one inherited from Newton and refined through centuries of classical thought, encouraged a very specific image of reality. Space was the stage. Matter was the cast. Objects had positions, trajectories, and definite identities. Forces acted between them, but the objects themselves remained the basic furniture of the universe. Even when science discovered atoms, electrons, and nuclei, the instinct remained the same. Reality was still imagined as a hierarchy of smaller and smaller entities. Quantum mechanics began to damage that image, but it did not destroy it completely. It gave us particles that behaved strangely, yes. Particles that could interfere, superpose, entangle, and refuse ordinary localization until measured. But the word particle survived, and with it survived a great deal of classical imagination. People still pictured tiny things, only now tiny things with weird habits. What comes next is more radical than that, because the more modern framework does not merely say that particles are strange. It suggests that particles are not fundamental in the first place, not as the deepest answer to what the world is made of, not as the final ontology, not as the true bedrock of being. And once that possibility is allowed in, the whole emotional structure of the universe changes. The world stops looking like a warehouse of objects and starts looking more like a choreography of appearances, less like a collection of self-contained bits of matter, more like patterns emerging from an underlying fabric that does not resemble matter in the old sense at all. That does not make the world less real. If anything, it makes it more difficult and more astonishing. Reality becomes less tangible to the imagination, while becoming more exact in the mathematics. This is one of the most beautiful and unsettling turns in modern physics. The closer we come to the fundamental level, the less the world resembles the pictures human intuition wants to keep drawing. The rock, the hand, the body, the air, the light, the space between things. All of it begins to lose the familiar texture of little bounded objects sitting side by side in a passive emptiness. And that matters for the question of being. Because if the world is not made of solid, independent chunks, then existence itself may not mean what we have unconsciously assumed it means. To exist may not be to stand alone as a finished thing with hard edges and permanent self-identity. It may be to arise as a pattern, to persist as a relation, to hold shape for a while within a deeper field of activity that does not belong to any single object at all. That idea can feel almost too abstract at first, but it becomes easier to hold if you let go of the demand that the universe must be picturable in ordinary language. Physics is under no obligation to comfort the imagination. It is only obligated to describe the world as faithfully as possible. And sometimes, fidelity to reality means surrendering the pictures that once made reality feel simple. So, the movement here is not away from science, but deeper into it. Measurement cracked the old confidence that properties are quietly waiting in place before we look. What comes now cracks an even older confidence, the belief that matter is made of little things, each carrying its own separate bit of existence inside itself. That confidence is about to become much harder to keep. At a certain point, the language of particles begins to mislead more than it helps. That sentence may sound strange because modern physics is full of particle talk. Physicists speak of electrons, photons, quarks, gluons, neutrinos, bosons. Particle accelerators are built to smash particles together. Detectors are designed to track particles. Entire branches of research are named after particle physics. So it is natural to assume that the deepest layer of reality is, quite literally, made of tiny objects. But that assumption does not survive the full development of modern theory. What survives is something more subtle. Particles remain useful. They remain measurable. They remain indispensable as practical language. But as a final answer to the question, what is the universe made of? They begin to dissolve. The more exact framework does not say that matter is built from little self-standing things moving around inside empty space. It says that the fundamental entities are fields, continuous physical structures extending throughout space, and that what we call particles are localized excitations of those fields. That difference is not cosmetic. It changes the ontology completely. In the older mechanical imagination, the world is built from pieces. Space is the container. Objects are placed inside it. They may collide, attract, or repel, but they remain the basic furniture of reality. Even after quantum mechanics arrived, much of that picture lingered. The particles became stranger. Yes, they could be delocalized. They could interfere. They could become entangled, but they still sounded like things. Quantum field theory is the point where that comfort finally breaks. In this framework, the electron is not a tiny bead with a private little existence of its own, traveling through an otherwise empty background. The electron is an excitation of the electron field. The photon is an excitation of the electromagnetic field. Quarks are excitations of quark fields. Gluons are excitations of the gluon field. The Higgs boson is an excitation of the Higgs field. Each field is present everywhere. Not in one region only, not in one atom only, everywhere. That is the first image the mind resists. A field is not a little object. It is not a hidden pebble at the bottom of matter. It is something spread out, continuous, and difficult to picture in ordinary language. The best everyday analogy is an ocean, but even that is limited. The ocean analogy can help because a wave is not a separate substance floating on top of water. A wave is what the water is doing in a certain region. The water remains the underlying reality. The wave is a temporary pattern within it. Quantum field theory says something like that, but more radical. The field is the underlying reality. The particle is the temporary pattern. An electron, then, is not a tiny marble made out of some deeper material. It is a quantized ripple in the electron field. A photon is not a microscopic pellet of light. It is a discrete excitation of the electromagnetic field. A particle is not a thing that sits inside a field like a boat sits on a lake. The particle is the field in a particular mode of excitation. That is why the field remains when the particle vanishes. If an electron meets a positron and the two annihilate, the electron does not reveal a deeper little core hiding beneath its own destruction. The excitation disappears. The field does not. The field was there before that electron appeared, and the field remains after that electron is gone. The field is fundamental. The particle is derivative. The field is what is there. The particle is what happens when the field is excited in a specific way. This is not poetic interpretation layered onto the equations after the fact. This is what the formalism itself leads toward. The historical path matters here because it shows how reluctant physics was to give up the older image. Early quantum mechanics still carried traces of the classical world. The equations were strange, but the conceptual furniture had not yet been fully replaced. Electrons were still imagined as objects of a kind, only now objects with probability amplitudes instead of neat deterministic paths. Quantum field theory went further. It did not merely make particles more mysterious, it demoted them. Paul Dirac played a foundational role in this transition. Later, Richard Feynman, Julian Schwinger, and Shinichiro Tominaga helped build the modern framework into something calculationally powerful enough to match experiment with extraordinary precision. Their work, along with the machinery of renormalization, turned quantum field theory into the backbone of the Standard Model, the most successful theory of elementary physics ever produced. Renormalization deserves a brief pause because it reveals something important about how deep this structure goes. When physicists calculate interactions among quantum fields, the mathematics naturally produces contributions from fluctuations at many scales, including ones that appear to blow up toward infinity. At first glance, that sounds like a failure, but renormalization provides a disciplined way to absorb those infinities into the observed values of quantities like mass and charge, leaving behind predictions that agree with experiment to astonishing accuracy. The results are not merely respectable, they are almost unnervingly precise. Quantum electrodynamics, the field theory describing light and charge particles, produces predictions for certain measured quantities that agree with experiment to more than 10 decimal places. In the history of science, very few achievements come close. This is not the sort of accuracy one gets from a vague metaphor. It is the accuracy of a theory that has touched something real. And what it touches is not a universe built from tiny hard pieces. It is a universe built from fields. That word everywhere is important and worth lingering on because it is one of the places where intuition begins to soften. If the electron field exists everywhere, then the electron in your body and the electron in a distant star are not two separate little substances in the deepest sense. They are two excitations of the same field, two localized expressions of one underlying entity, two ripples, if you like, in a single continuous fabric. That does not mean the electrons are identical only in a vague philosophical sense. It means they are literally excitations of the same kind of field, governed by the same structure, the same charge, the same spin, the same mathematical identity. Their sameness is not an accident. It is built into the ontology. There are not billions upon billions of utterly separate electron substances scattered across the cosmos. There is one electron field, and what we call many electrons are repeated excitations of that one field. The same is true for photons, the same for quarks, the same for every type of elementary particle in the Standard Model. Already that begins to change the emotional architecture of existence. Because if what we call a thing is really a localized excitation within something more fundamental, then being starts to look less like isolated self-possession and more like temporary expression, less like independent material ownership, and more like structured appearance. A particle is real, certainly, but its reality is not the reality of a miniature brick. It is the reality of a pattern. And a pattern is not unreal because it depends on an underlying medium. A wave is real. A flame is real, a whirlpool is real, but none of those are little separate substances floating free of what gives rise to them. They are dynamic organizations within something deeper. Quantum field theory invites us to see the entire material world in something like that way. Not as illusion, not as fantasy, not as mere appearance in the dismissive sense, but as appearance in the precise sense of structured emergence. This is why the phrase particle can become dangerous if held too tightly. It encourages the imagination to keep sneaking back toward the old furniture of the world. Tiny balls, tiny points, tiny pieces of matter. But quantum field theory asks for a different mental posture. It asks us to stop imagining the universe as a heap of objects and to begin imagining it as a continuous field structure whose excitations present themselves to us as the particles we detect. Even the word detect becomes richer under this light. A detector does not pull a tiny hidden marble out of invisibility. It couples to a field excitation. It registers a localized event generated by the interaction of fields. The screen lights up. The counter clicks. The chamber traces a path. What appears is concrete and measurable, but the underlying ontology is no longer the ontology of little independent things. It is the ontology of fields giving rise to events. And once that is seen, ordinary matter begins to feel less settled in a surprisingly beautiful way. Your body is not, at bottom, a pile of miniature objects stacked together like grains of cosmic sand. It is a layered organization of excitations in multiple interacting fields. The chair, the wall, the air, the sunlight, the glass of water, all of them are stable patterns in a deeper field-like order. This does not make reality less physical. It makes physicality stranger than classical intuition ever allowed. The universe is not made of objects first and relations second. At the deepest level, the relations are built into the fields themselves, into the way excitations arise, propagate, and interact. Matter is no longer best understood as substance in the old sense. It is activity taking form. It is field behavior becoming local enough, stable enough, and quantized enough to appear to us as a thing. That is why the phrase "particles are not things" is not an attempt to be mystical. It is an attempt to be exact. They are not things in the old hard material sense. They are excitations. And once that is absorbed, even a little, the world begins to lose some of its apparent solidity long before we ever talk about the vacuum or empty space or the restless energy hidden in what once seemed like nothing at all. There is an old image of empty space that still lingers in the mind long after physics has outgrown it. It is the image of a blank stage. Matter and radiation are removed. The particles are gone. The light is gone. The room is cleared, and what remains is simply nothing. A silent backdrop. A container with no contents. A kind of physical zero. That picture is natural. It is also, as far as modern field theory can tell us, false. Because once fields replace particles as the fundamental ontology, emptiness becomes much harder to define. If fields pervade all of space, then even a region with no particles in it is not a region with no reality in it. The absence of particles is not the absence of the field, and if the field remains, then what we call vacuum is no longer absolute nothingness. It is the lowest energy state of a field, not the non-existence of the field itself. That distinction changes everything. In classical physics, a vacuum can be imagined as perfect stillness. Remove the objects, remove the waves, remove the disturbances, and the medium rests. But quantum theory does not allow that kind of perfect quiet. The reason goes back to the uncertainty principle, which most people first encounter as a limit on how precisely you can know position and momentum at the same time. In field theory, a related principle applies to the field itself and to its rate of change. A field cannot be pinned to exact zero amplitude and exact zero motion simultaneously. The mathematics does not permit perfect rest. So even in its ground state, the field is not motionless. It flickers. Not in a dramatic visual sense, not in the cartoon way popular science sometimes suggests, but in a precise quantum sense. There are irreducible fluctuations in what we call the vacuum, tiny temporary deviations, restlessness at the floor of reality. The the field never becomes a dead sheet of nothingness. It retains a minimum activity that cannot be removed because the structure of the theory forbids complete stillness. This is what people mean when they talk about vacuum fluctuations. Sometimes the language becomes more vivid, and physicists speak of virtual particles. An electron and positron appear, then vanish. A photon briefly contributes and disappears. A particle-antiparticle pair flickers into and out of the vacuum too quickly to be directly isolated as ordinary observable particles. This language can be useful, but it also has to be handled with care. Virtual particles are not tiny, durable objects popping into existence like fireflies in a dark room. They are features of the quantum field calculations, temporary contributions associated with the restless structure of the vacuum itself. Still, the essential point remains. The vacuum is not empty in the old classical sense. And this is not merely a verbal flourish or a philosophical embellishment. The vacuum leaves fingerprints. It alters measurable quantities. It participates in real experiments. If it were only mathematical decoration, the theory would drift away from reality. Instead, the opposite happens. The more seriously physicists take the active vacuum, the more accurately the theory matches the world. One of the most famous examples is the Lamb shift. In a hydrogen atom, the energy levels predicted by a simpler treatment do not line up perfectly with what is measured. There is a tiny discrepancy. Quantum electrodynamics explains this by accounting for the interaction between the electron and the fluctuating electromagnetic vacuum around it. The electron is not sitting in isolation inside a clean, dead emptiness. It is immersed in a sea of quantum activity, and that activity slightly shifts the energy levels. The measured result matches the theory because the vacuum is doing something. Another celebrated example is the anomalous magnetic moment of the electron. This is one of the most precisely tested predictions in all of science. The agreement between theory and experiment is almost absurdly good, extending to astonishing decimal precision. That calculation includes contributions from vacuum fluctuations, from the cloud of quantum activity surrounding what might naively be imagined as a simple particle. The electron, in other words, is not a bare isolated object. It is dressed by its interactions with the fields around it, including the vacuum itself. That alone would already be enough to overturn the old intuition. But there is an even more dramatic case, one that almost seems designed to humiliate the word empty. It is called the Casimir effect. Take two uncharged metal plates and place them extremely close together in a vacuum. No classical electric attraction should be present if the setup is arranged properly, and yet the plates are pushed toward one another. Why? Because the quantum vacuum between the plates is not identical to the quantum vacuum outside them. The plates restrict which field modes can exist between them. Outside, a broader range of fluctuations is allowed. Inside, the allowed modes are more limited. That imbalance creates a measurable pressure, a force emerging from what older intuition would have called nothing at all. Empty space pushes. That sentence should be enough to permanently disturb the classical imagination. The vacuum is not passive. It is not merely where things happen. It has structure. It has consequence. It contributes to the physical behavior of matter. When the Casimir effect is measured, what is being revealed is not a metaphor. It is a real force arising from the difference in the quantum field structure of apparently empty space. And once that fact settles in, something deeper begins to open. Because if nothingness is active, then the line between being and non-being becomes stranger than common sense expected. The vacuum is not a simple absence. It is the lowest accessible state of a system that still possesses irreducible energy, irreducible fluctuation, irreducible potency. That word potency matters here. A classical vacuum is sterile. A quantum vacuum is fertile, not in a mystical sense, in a formal, physical sense. It is a domain from which excitations can arise, into which they can vanish, and through which measurable effects are continuously mediated. What once looked like emptiness becomes a reservoir of structured possibility. This is one reason modern physics can feel oddly close to metaphysical language without ever ceasing to be physics. The vacuum is not a theological void. It is not divine presence. It is not a spiritual field. But it does quietly erase the crude opposition between something and nothing that ordinary speech tends to rely on. The vacuum is the nearest physical theory gets to emptiness, and even there, at the supposed floor of being, the universe refuses to become simple. There is also a larger problem waiting behind all of this, and it is one of the great embarrassments of theoretical physics. If vacuum fluctuations are real, then the vacuum carries energy. But when physicists try to estimate the vacuum energy in the most straightforward way, the answer comes out catastrophically wrong compared to what cosmology seems to observe. Not slightly wrong, not 1 or 2 orders of magnitude wrong, wildly, almost absurdly wrong. And yet the observed vacuum energy is not zero. The accelerating expansion of the universe suggests that empty space really does carry a tiny positive energy density, something like what is often called dark energy. So on the one hand, the vacuum undeniably matters. On the other hand, our theoretical understanding of its energy remains deeply incomplete. This is the cosmological constant problem, and it is one of the places where the smooth success of quantum field theory collides with a genuine conceptual abyss. That abyss is worth mentioning because it keeps the tone honest. The vacuum is not empty, yes, that much is secure. But what the vacuum finally is, why its energy has the value it appears to have, and how that connects to gravity and cosmology remain open questions. The deeper we go into nothing, the less final our understanding becomes. And that is the real mood of this part of the story. Not triumph, not mystical exaggeration, not cheap astonishment, something quieter. The quiet realization that empty space is not empty. That beneath every object, beneath every atom, beneath every flash of light, there is not a dead backdrop, but a restless quantum ground, a field-filled substrate that does not fall silent even when no particles are present, a vacuum that trembles, influences, contributes, and refuses to become a mere blank. Once that is seen clearly, the world changes texture again. The old picture of matter sitting inside emptiness no longer works. Matter emerges from fields, and even the absence of matter remains physically alive. The stage is no longer separate from the play. The emptiness is no longer empty, and the ordinary confidence that nothing must be simple begins to fade. Because in modern physics, even nothing has structure. Take an ordinary stone in your hand and the illusion feels complete. It feels dense. It feels compact. It feels final. Your fingers press against it and receive an answer immediately. Resistance. This, more than almost anything else in daily life, is what solidity means to us. Something is there. Something occupies space. Something refuses to let something else pass through it. The rock seems to be the definition of a self-contained physical object, and yet almost every part of that impression becomes strange the moment physics looks closely. The first surprise is scale. An atom is mostly empty space. That sentence is familiar now, perhaps too familiar, and because it is familiar, it has lost some of its force, but it is worth letting it become strange again. If an atom were expanded to the size of a football stadium, the nucleus would be something like a tiny marble near the center. The rest of the stadium, the field, the seats, the air above it, would be the region in which the electron cloud is spread. Not little hard balls orbiting like miniature planets, but a diffuse quantum structure described by probabilities and field excitations. So, when you touch a rock, your hand is not meeting a densely packed wall of miniature billiard balls. It is not a little lattice of tiny stones bumping into another little lattice of tiny stones. Your hand is mostly empty space. The rock is mostly empty space. Two vast, structured regions of almost nothing approach one another, and yet they do not pass through each other. Why? Not because emptiness suddenly became full of solid bricks at the last moment, and not because matter, at bottom, secretly recovered its old classical hardness? The answer is more interesting than that. The resistance you feel is the result of quantum rules and electromagnetic interaction. What feels like solid contact is, in a very real sense, a refusal built into the architecture of matter itself. A large part of that refusal comes from the Pauli exclusion principle. This principle says that no two identical fermions, such as electrons, can occupy the same quantum state at the same time. That sounds abstract at first, but its consequences are everywhere. As the electron clouds in your hand approach the electron clouds in the rock, the allowed quantum states become increasingly constrained. The electrons resist compression into the same configuration. The result is not a gentle reluctance. It is a steep, overwhelming resistance that rises rapidly as the structures are pushed closer together. Alongside that, there is electromagnetic repulsion. Electrons carry negative charge, and like charges repel. So the contact between hand and stone is not a meeting of solid pieces in the old mechanical sense. It is a field-mediated resistance between charged quantum structures, reinforced by the exclusion principle. The sensation of hardness is what those rules feel like at human scale. This is one of the most beautiful reversals in all of physics. Solidity is real, but it is not fundamental. It is an emergent effect. It is what quantum fields and quantum statistics look like when translated upward into the language of touch. The rock is not solid in the old sense. The rock behaves solidly. That distinction matters because it loosens another old instinct. We tend to think that if something feels dense and massive, then its mass must come from some inner stockpile of material substance. But here too, the deeper story is less intuitive and more elegant. When people hear about the Higgs field, they often come away with a simplified slogan: the Higgs gives everything mass. That is not entirely wrong, but it is incomplete in a very important way. The Higgs field does give intrinsic mass to certain elementary particles. Without it, electrons and quarks would not have the masses they do. The discovery of the Higgs boson at CERN in 2012 confirmed a central part of that framework. So, the Higgs matters enormously. But if you take a proton, the sort of object that sits inside every atomic nucleus in ordinary matter, and ask where its mass comes from, the answer is more surprising. The masses of the quarks inside the proton account for only a small fraction of the proton's total mass. The overwhelming majority comes not from the bare masses of its ingredients, but from the energy of the strong force field binding those ingredients together. Inside the proton, quarks are held in an intensely dynamic state by gluons, the carriers of the strong interaction. These gluons are themselves massless, and yet the energy bound up in their motion and interaction contributes, through Einstein's relation between mass and energy, to almost all of the proton's mass. In other words, what you call mass is not simply a pile of substance. It is, to a remarkable degree, organized energy. That means your weight is not what common sense thinks it is. You are not heavy because you contain a lot of little dense nuggets of matter in the old-fashioned sense. You are heavy largely because energy is trapped in stable quantum structures. The matter in your body owes most of its mass to the restless binding energy inside protons and neutrons, not merely to some static inventory of elementary pieces. This gives the familiar world a very different emotional tone. The table, the wall, the chair, your own hand, all of it seems so fixed and settled from the outside. But beneath that calm appearance is an astonishing amount of structured activity, fields interacting, charges repelling, quantum states refusing overlap, binding energy locked into tiny regions with enough intensity to become the mass of ordinary things. The world is not built from tiny hard pellets. It is built from stable forms of resistance and trapped vibration. That phrase can sound poetic, but it is also exact in the way that matters. Matter is not an illusion. The rock is real. Your hand is real. Pain is real if you strike one against the other. But the reality involved is not the old reality of indivisible little blocks. It is the reality of field excitations, quantum restrictions, and energy taking durable shape. And once that is seen clearly, the sentence, "nothing is solid," stops sounding like a mystical slogan and begins to sound like a technical truth. Not because the world is unreal, but because its reality is more layered than the sense's first report. Solidity belongs to the level of experience and macroscopic behavior. Beneath that level, what you find is not little hard things, but quantum structure all the way down. The rock remains in your hand, but what it is has changed. Einstein never used the word absurd lightly. He had already changed physics twice. He had rewritten our understanding of space, time, light, energy, and gravity. He was not a man easily rattled by strange ideas. But there was one consequence of quantum mechanics he could not accept, not because it was mathematically sloppy, but because it seemed to violate something deeper than convenience. It seemed to violate the very shape of physical reality. The problem was entanglement. To understand why Einstein found it so disturbing, it helps to begin with the picture of the world that classical physics quietly trained us to trust. The world appears to be made of separate things. A stone is here, a tree is there, a star is far away. Objects occupy their own regions of space, carry their own properties, and influence one another through signals or forces that travel across the distance between them. Even when one object affects another, the separation remains meaningful. Distance is real, independence is real, locality is real. What happens here should not instantly determine what happens there. Einstein believed that any sensible physical theory should preserve that basic structure. He also believed in realism, the idea that physical properties exist whether or not we happen to measure them. The moon is there when no one looks. A particle has whatever properties it has before an experiment reveals them. Measurement may uncover reality, but it should not be responsible for manufacturing it. That conviction sat deep in Einstein's bones. In 1935, Einstein, Boris Podolsky, and Nathan Rosen published a paper that was meant to expose what they saw as a fatal incompleteness in quantum mechanics. The setup later became known simply as EPR. The core idea was deceptively simple. Imagine two particles created together in such a way that their properties are linked. If one turns out one way, the other must turn out the opposite way, then separate them by a great distance. Now comes the question. If you measure one particle and instantly know the corresponding property of the other, what explains the correlation? Einstein thought there were only two reasonable options. Either the second particle's property was already there all along, merely waiting to be revealed, or some influence traveled from the first measurement to the second particle faster than light. The second option violated relativity and locality. Einstein refused to accept that, so he chose the first. Quantum mechanics, he argued, must be incomplete. The particles must carry hidden variables, pre-existing facts that the standard formalism simply failed to describe. This was the famous spooky action at a distance, and Einstein did not mean it as praise. For a long time, the argument remained a philosophical wound more than an experimentally settled matter. People could line up on different sides according to temperament. Some accepted the strange correlations as a sign that quantum theory was pointing beyond classical common sense. Others hoped that deeper hidden variables would eventually restore locality and realism beneath the quantum surface. Then John Bell arrived. In 1964, Bell did something extraordinary. He took a dispute that had seemed almost metaphysical and turned it into mathematics sharp enough to test in the laboratory. Bell asked a very precise question. If Einstein were right, if the particles really did carry hidden instructions established in advance, and if no influence could travel faster than light, then how strong could the correlations between the particles possibly be? He derived an inequality, now called Bell's inequality, that any local hidden variable theory must satisfy. This was not vague. It was not philosophical mood. It was a measurable limit. If the world is both locable and realistic in Einstein's sense, then the correlations between entangled particles cannot exceed a certain bound. Quantum mechanics predicted that they would. That is what made Bell's theorem so devastating. It did not merely say that quantum mechanics is strange, it said that strange and classical are no longer equally available options. There is an experimental line in the sand. Either the world behaves within the limits allowed by local realism, or it does not. If it does not, then Einstein's preferred picture cannot be the full truth. At first, this remained mostly a theoretician's challenge. Then the experiments began. John Clauser carried out one of the earliest serious tests in the 1970s. His results already pointed toward the quantum prediction. The correlations violated Bell's inequality. But the early experiments had loopholes, technical gaps that allowed defenders of local realism to keep hoping. Perhaps the detectors were biased. Perhaps the measurement settings were not chosen independently enough. Perhaps, somewhere in the machinery, a classical explanation could still hide. Then came Alain Aspect in the early 1980s. Aspect designed experiments in which the measurement settings were changed, while the entangled photons were already in flight. Too late for any ordinary light-speed signal to coordinate the outcomes in the classical way Einstein would have wanted. Again, the quantum prediction held. Again, Bell's inequality was violated. Again, the world refused to behave like a collection of separated objects carrying pre-written local properties. And the experiments did not stop there. Over the following decades, physicists kept tightening the net. Better detectors, faster switching, longer distances, cleaner sources, cleverer designs. Anton Zeilinger and others extended entanglement experiments across larger and larger separations, eventually into regimes that had once sounded like science fiction. One loophole after another was narrowed, closed, or rendered increasingly implausible. In 2022, Clauser, Aspect, and Zeilinger were awarded the Nobel Prize in Physics for work that helped establish this strange quantum structure beyond reasonable doubt. Bell inequalities are violated. That sentence is easy to say and difficult to absorb, because what it means is not merely that quantum mechanics is weird. It means the universe is not locally real in the way Einstein hoped. At least one of the two cherished principles must give way. Either physical properties are not fully definite before measurement, or the world permits a kind of non-local connection that cannot be understood as ordinary signal transfer through space, or both. The old union of locality and realism cannot survive intact. It is important to say what this does not mean. Entanglement does not let you send messages faster than light. You cannot use it as a cosmic telegraph. When one observer measures 1/2 of an entangled pair, they do not gain the power to control the result in a way that transmits usable information to the other side. The outcomes are correlated, yes, but the correlation only becomes visible when the measurement records are later compared through ordinary classical communication. So, relativity is not casually smashed, and yet the deeper point remains untouched. The correlation exists in a way that cannot be explained by local pre-existing properties alone. The two particles are not behaving like fully independent little things that happen to fly apart and carry private identities with them. They are behaving like components of a single quantum state whose structure is more fundamental than the distance between them. That is why entanglement matters so much for the question of being. It is not just another exotic quantum effect. It is a direct challenge to separateness as a basic category. The world does not seem to be made of isolated units first and relationships second. In entanglement, the relationship is written into the state from the start. The parts do not come fully packaged with self-contained properties waiting quietly to be uncovered. What is true of one depends, in a deep formal sense, on what is asked of the other. Einstein wanted a universe built from local facts. Bell showed that such a universe cannot reproduce what experiment actually reveals. And so, a new possibility begins to take shape. Perhaps distance is not the deepest divider we thought it was. Perhaps what we call two things can, under the right conditions, be one structure expressed across two locations. Perhaps the world is less like a pile of separate objects, and more like a web whose connections run deeper than space itself seems to advertise. That is not mysticism. That is what the experiments forced us to face. What makes entanglement so hard to live with is not just that the correlations are strong, it is that they refuse to behave like ordinary connection. In everyday life, if two things are connected, we know roughly what that means. A rope ties them together. A signal travels between them. A force reaches across the space that separates them. One pushes, the other responds. Even if the mechanism is invisible, we still imagine some chain of influence moving from here to there through the distance in between. Entanglement is not like that. That is why it survived Einstein's objection and still remains one of the most unsettling features of modern physics. The problem is not merely that two particles can be correlated. Classical physics allows correlation. If two gloves are placed in separate boxes and sent to opposite sides of the world, opening one box and finding the left glove tells you instantly that the other box contains the right glove. But nothing mysterious has happened. The properties were fixed all along. The information was only hidden from you. Entanglement is different because the particles do not behave as though they were carrying pre-written answers in advance. They behave as though the state belongs to the pair, not to each particle separately. That distinction is the entire heart of the matter. When two particles are entangled, the mathematics does not give each one a fully independent description of its own. It gives one joint state for the combined system. The pair is primary. The separate pieces are secondary. You can pull them apart in space, send them to opposite ends of a laboratory, opposite ends of a city, even, in principle, opposite ends of the observable universe, and the formal structure still treats them as parts of one indivisible quantum description. This is why entanglement feels so unlike the ordinary world. Distance does not erase the unity of the state, but that still leaves an important caution. Entanglement does not allow faster-than-light messaging. That point matters because it is often the first place the imagination runs away from the actual physics. If two entangled photons are separated and one is measured, the result at the other side is correlated with it, but no usable message has been sent. The observer measuring the second photon does not receive a controllable signal that says, "The first observer has chosen this." They only see a local outcome. The deeper correlation becomes visible only when both observers later compare their data through ordinary classical communication, which still obeys relativity. So, entanglement gives connection without signaling. That phrase is one of the strangest in all of science and one of the most precise. There is no hidden telegram crossing the void. No tiny superluminal messenger slips through space to carry the instruction from one particle to the other. The connection is already built into the shared state. What appears across distance is not a transmitted command, but a single formal structure revealing itself in two places. That is why the old picture of two separate things becomes so unstable here. Classical thinking wants to begin with independent objects, and then explain how they interact. Entanglement asks us to begin somewhere else. It suggests that, in some cases, the relation is more fundamental than the relata. The joint state comes first. The apparent separateness comes later. This is where the emotional meaning of entanglement begins to deepen. Up to this point, the story has already stripped away several old comforts. Measurement was not merely passive revelation. Matter was not made of tiny solid things. Vacuum was not empty. Solidity was emergent. Now another intuition begins to soften. The intuition that separateness itself is basic. Because entanglement does not look like an accidental linkage between two otherwise complete objects. It looks more like a reminder that what we call objects may not be complete on their own in the first place. The consequences of that idea extend beyond thought experiments. Quantum teleportation is one of the clearest demonstrations. The name is misleading if taken literally. No chunk of matter is dematerialized here and rematerialized there, like something from science fiction. What is transferred is the quantum state. Using entanglement plus a classical communication channel, the exact state of one system can be reproduced in another distant system, while the original is no longer there in the same form. The state does not travel through the intervening space like an ordinary object moving from point A to point B. It is reconstructed through the entangled connection and a limited amount of classical information. This sounds fantastical until you realize it has been demonstrated experimentally. And once again, the lesson is not that reality is magical in a childish sense. The lesson is more disciplined than that. The world is not organized as neatly around separateness as classical intuition expected. Quantum information can be distributed, shared, and reassembled in ways that force us to rethink what it means for something to be here rather than there. Even more unsettling is the fact that entanglement is not a rare jewel found only in highly exotic laboratory setups. In a sense, it is everywhere. Every sufficiently intimate quantum interaction can create it. Photons scatter, atoms collide, molecules couple, systems become correlated. The universe, at its deepest level, is not a pile of self-enclosed objects occasionally brushing against one another. It is more like a web of interactions in which independence is often approximate rather than absolute. Of course, in the human scale world, decoherence quickly hides most of this unity from us. Thermal noise, environmental interaction, and the sheer complexity of macroscopic systems wash out the delicate quantum structure that would otherwise appear more directly. That is why tables remain tables and why you do not feel yourself as a superposed node in a cosmic quantum fabric. The classical world is robust. Separateness works as an approximation, but an approximation is not the same thing as a foundation. And that is the deepest correction entanglement offers. Separation may be useful. Separation may be experientially obvious. Separation may even be unavoidable in the practical world of ordinary life. But at the level where physics is forced to speak most carefully, it no longer seems fundamental. The deeper reality is not made of isolated pieces first and connections second. Quite often, the connection is there from the beginning, and what we call separate things are the local faces of a more unified underlying state. That is not a mystical slogan. It is simply what the mathematics and the experiments keep insisting on. There is an even more radical possibility waiting behind entanglement, and it begins with a quiet reversal of the way most of us picture physics. We imagine space as the stage and everything else as the performance. Particles move through space, fields fill space, forces act across space. Space comes first, and the drama of the universe unfolds inside it. But some of the deepest ideas in modern theory suggest that this order may be backward. Space itself may not be fundamental. It may be something that emerges. One of the most provocative expressions of this idea is the conjecture known as EAR equals EPR. The initials are a kind of historical echo. EPR refers to the entanglement problem Einstein, Podolsky, and Rosen laid out in 1935. ER refers to Einstein-Rosen bridges, what we now informally call wormholes. For decades, these looked like completely different ideas. One concerned quantum correlation. The other concerned strange tunnels in space-time geometry. Then came a daring suggestion from Leonard Susskind and Juan Maldacena. Perhaps these are not separate mysteries at all. Perhaps entanglement and geometric connection are two aspects of the same deeper structure. In that view, two entangled systems are not linked across space by some hidden signal. They are connected more directly through the underlying geometry itself, in a way our ordinary picture of distance does not capture. This does not mean every entangled particle pair contains a traversable science fiction tunnel. The proposal is subtler than that. It means that the relationship between quantum information and space-time geometry may be far deeper than classical intuition ever imagined. A similar shift appears in the holographic principle. This idea suggests that the information content of a region of space may be encoded not throughout its volume in the way common sense expects, but on its boundary. That sounds abstract, but its implication is extraordinary. The three-dimensional world we experience may, at some level, be an emergent projection of a deeper informational structure. Then came an insight from Mark von Ramsdonk that made the whole picture even more striking. In certain theoretical models, if you reduce or remove the entanglement linking parts of a quantum system, the corresponding geometry begins to come apart. The space-time no longer holds together in the same way. The connection is not decorative, it looks structural. Entanglement behaves less like something happening inside space, and more like part of what allows space to exist as a connected thing at all. That possibility changes the emotional scale of everything we have said. If it is true, then separateness is not only incomplete at the level of particles, it is incomplete at the level of space itself. Distance may not be the deepest fact. Geometry may not be the deepest fact. The stage may be woven from the very quantum relations we once imagined were merely taking place upon it. Space would no longer be the silent container of reality. It would be one of reality's outcomes. And if that is even partly right, then the universe is stranger than the old conflict between wave and particle ever suggested. It means that what looks like a world of things arranged in a ready-made arena may, at bottom, be a world in which relation comes first, and the arena itself is born from the relation. And so we arrive at the edge of the question. Not the edge of physics, because physics will go on. New experiments will be built. New formalisms will be tested. New interpretations will rise, sharpen, and perhaps fall away. But the edge of something older and quieter than that. The edge of what it means to exist at all. There is no official quantum law of being, no equation in a textbook with that title, no single theorem that tells you, once and for all, what existence is, why reality appears, or why you are here inside it. Anyone who says physics has already solved that question is speaking too quickly. But physics has changed the shape of the question forever. It has shown us that matter is not solid in the way it seems, that particles are not tiny self-standing things, but excitations of fields. That empty space is not empty. That measurement is not obviously passive. That separateness may not be fundamental. That what looks simple at human scale becomes relational, unstable, and deeply structured when followed down to the roots. And if all of that is true, then being begins to look less like a noun and more like a process, less like possession and more like participation, less like a fixed object standing alone and more like a temporary coherence in a deeper web of fields, interactions, information, and form. That does not prove the old contemplative traditions were secretly doing quantum mechanics. They were not. And quantum mechanics does not prove theology, mysticism, or metaphysics in any simple way. But the structural echo is hard to ignore. The solid is not solid. The empty is not empty. The separate is not separate. Reality, at depth, is stranger and more interwoven than the surface suggests. Maybe that mystery is not a flaw in the world. Maybe it is one of its deepest features. The fields remain. The vacuum stirs. Outcomes appear, relations hold, and the question itself stays awake, quiet, and luminous, beneath everything we think we know. So, if you enjoy drifting with me through this slower, deeper side of physics, gently like the video, subscribe to the Quantum Slumber, and tell me in the comments where you're listening from tonight. I always love seeing how far these quiet journeys travel. Thank you for spending this time with me. And now, whatever thoughts are still softly turning in your mind, you can let them go one by one. Let the questions loosen. Let the edges blur. Let the mystery stay unsolved for tonight. And let sleep come gently. Good night.